Hello everyone, we're going to be talking about velocity and speed. Let's go back to those two videos we saw in the last lecture. In this video we took a series of data points. We found that Dr. Andreessen's position increased with time. We can get actually his velocity during this time interval. So what we're first going to define is this average velocity. So this is v with a bar on top. This is defined as x final minus x initial over delta t. So this top looks really familiar because this is the displacement. So velocity you could also consider as the displacement in the amount of time that displacement occurred. So here we have the average velocity. So let's go ahead and calculate that. So here we have 10 meters minus 0 meters. The amount of time that it took was this 1.4 seconds. So this gives us just over 7 meters per second. Let's consider one more video here. Alright, to better describe the motion that's going on here, we could also calculate the average velocity. So we can consider the average velocity over the entire interval. So between t equal 8.5, I was at 10 meters. My initial displacement was at 0 meters. So this occurred between 8.5 seconds and about 2 seconds. So this gives us an average velocity of 1.5 meters per second. So this is the average velocity, 1.5 meters per second. But this gives us not quite all the information that we could extract from this video. Here we know that there was some region of time in which I was stopped. So we know that this average velocity is kind of smearing out some of the action that was, or inaction that was going on. So let's split this up into 3 different regions here. Alright, so here we have region 1, and some region 2, and then a region 3. And let's calculate the velocity for each of these regions. Alright, so in region 1, my average velocity was 7 meters minus 0 meters. And this occurred between about 4 seconds and that 2.5 seconds. Alright, and this gives me an average velocity during that region of about 4.7 meters per second. So you can see that this number is much bigger than this average velocity over the whole time window, because this includes this region where I was pausing. So in this region 2, we can also calculate my average velocity during region 2 is not as interesting because we have 7 minus 7 over 7 minus 4, and that just gives us a 0. And in region 3, we're going to have 10 meters minus that 7 meters all over this 8.5 minus 7. So we're going to get about 2 meters per second. So there's just a few things here that I'd like to bring to your attention. One again is that this average velocity over this whole time window is this 1.5 meters per second. And then I'd like to contrast that with these 3 measurements that we made of the velocity during each of these 3 regions. This 4.7, a 0, and a 2. And you notice that this one, the one that we took over the whole time window, is somewhere in between all of these. So when we took this measurement over this big delta t, 8.5 to 2, what we're doing is we're smearing out all this action that's going on for the rest of the video. So we have this average velocity. I'm just going to write the equation again. It will help illustrate what's going on. It's the change in displacement and the change in time. So what we notice is that if we let this delta t get smaller, what we end up doing is picking up a little bit more of whatever is going on here. If we let delta t get very big, we end up smearing out some of the action that's going on. So let's go look at this velocity as a graph. So we looked at Dr. Andreessen's velocity on a graph. Here we have his speed, and his speed was that 7 meters per second. And then we look at mine. We calculated this 4, 0, and a 2. And we could also look at Mr. Orange's fictional data from last lecture we calculated. And his will give us 4 and a -2 and then about a 6. So here is the instantaneous velocity as a function of time. So the difference here is that we have the average velocity, delta x, versus delta t. And then the instantaneous velocity is going to be v without this bar on top. Is actually going to be the derivative of x with respect to time. And how do we get between these two is actually we're letting this delta t get very small. And then that will give us this delta t. So remember from the last slide that I just showed you, when we looked at my average velocity over this whole time window, we ended up with about 1.5. And so that would show something like this. Whereas if we look at my instantaneous velocity as a function of time, we get a curve that has some steps in it that correspond to where these 3 different regions are, 1, 2, and 3. So here we have the derivative of x with respect to time. So the velocity is the slope of this position versus time plot. So here we have one slope in region 1, which corresponds to this value here. So this is my region 1. Sorry. And we can see the same thing in region 2, where the slope is 0. And then in region 3 over here, where my speed picks back up to about 2 meters per second. So let's consider one more case of average velocity, instantaneous velocity that'll help clear a few more things up. So let's have one more curve here. And in this one, we don't have some simple straight line plot. Here we have a curved function. We can write this out as 4.9 t squared minus 0.2, and the units are in meters. So this curve is actually quadratic. It's curving up like this, and we could look at the average displacement, and so we can calculate this x. We can just look at over the time interval, this 0.3, so x final minus x initial over delta t, and this is going to give us 0.3 minus a negative 0.2, and the time that it took to do this is 0.3 seconds. So then from this we can get the average velocity over this time period. And so we could get a little bit more information by looking at what is the instantaneous velocity, and this is dx dt. So in order to do this, we can take the derivative of this function. So we're going to d by dt of this 4.9 t squared minus 0.2. When we take the derivative of this, we end up with 9.8 t. And so actually the velocity increases linearly with time. So we can make a plot of this function, and you can see that the velocity increases with time, just like what we predicted. Alright, so let's work out a problem. Here we have three different runners, P, Q, and R. We're each running a 5K race. P can run it in 15 minutes, R runs it in 20, and R runs it in 25 minutes, Q runs it in 20 minutes. Each are running at a constant speed. So when runner Q crosses the 1K mark, what is the distance between P and R? So let's draw a real quick description here. We know that we have three different runners, and each of them are running at a different speed. They start here at x equals 0. What we want to know is when P is at this 1K mark, what is the distance between Q and R? So let's break this down into a few more steps. We have some good information here. One is that each of them are running at a constant speed, and we can actually figure out each of their speeds. So let's work out VP. And so this is going to be this 5K. They run 5K in 15 minutes. And so this is going to give me 1/3 kilometers per minute, just to simplify this down. And we can do the same for Q. He's going to be 5K in 20 minutes. And so that's going to give me 1/4. And then now we have VR. It's going to be 5 kilometers in 25 minutes. That gives me 1/5 kilometers per minute. So now I have each of their average velocities during the race. So now let's, we've got the position of P at 1K. And so what we want to know is what's the distance. So this is some snapshot in time that we took. So as soon as P crosses this 1K, what is the distance between Q and R? So let's find out what that time is when P crossed that mark. So what is this T? Alright, so the way that we look at this is that distance equals the velocity times the time that you covered it in. Another way to get this relationship is by looking at this average velocity, right? We said average x over dt. We can see that this is just a rearrangement of this. So then let's solve for this t. So this t is going to be 1 kilometer when P was at 1 kilometer. Then now we are going to divide that by his velocity. So that's 1/3 km per minute. And these kilometers will actually cancel out. What we're going to get is 3 minutes. So P actually crosses this 1K mark at 3 minutes. So what are the positions of Q at 3 minutes? And so we just need to multiply VQ by T. And so this is going to be 1/4 kilometers per minute times 3 minutes. We can see that the minutes cancel out, and so this is going to be 3/4 kilometer, or 0.75 kilometers. And we can work out the same thing for R. So VR times T is going to be 1/5 kilometers per minute times the same 3 minutes. We want to know his position at that same time. So we end up with 3/5 kilometer. So this is going to give me 0.60 kilometers. So then these are the displacement of Q and R after when P is at 1 kilometer. So then what is the distance between them? We just subtract these two, and we're going to end up with this 0.15 kilometers.